So as we are saying that, we can see that we have different tangents, and we can actually generate a set, and this is what motivates us to define a tangent space in the first place. So let's go down to the definition of a tangent space. So tangent space definition. This tangent space is a space on a manifold. So this is a space on a particular point on a manifold. By on a manifold, we mean at a particular point. That contains all the possible tangent vectors that passes through that point. And again, graphically, it would look something like this. If this is our manifold and this is the point of interest, then a tangent plane would look something like this. And if this is our manifold, which is denoted with capital M, then the tangent space would be denoted as TP of M. The P is the point, and this tells you that if you have an element, let's say V, that belongs to TP of M, that means this V or this tangent vector belongs to the tangent space of a point P, and this point itself is residing in the manifold. Alright, so why do we bother even defining these things, right? Because it turns out that to define a vector field, we will need these ideas, because you cannot define a vector on a manifold itself. To define the vectors, you need those tangent spaces. These tangent spaces are the vector spaces. In fact, there are manifolds that exhibit both the behaviors of manifold itself. I mean, there are general spaces which exhibits the behavior of manifolds and vector spaces, but not all the manifolds show this behavior. So that's why we need to make these two spaces distinct, so that when we deal with more general type of manifolds in future, we don't get confused. And an example that there are spaces which exhibit both of the behaviors would be our familiar Cartesian coordinates. It's a manifold, and at the same time it's a vector space, but yet we want to keep these definitions distinct so that we don't get confused. Okay, now since we can define vectors, we can define tangent spaces. Now let's try to define a vector field. So from very rough idea or very basic vector calculus, you know that a vector field points towards a distribution that tells you that if you have some space like this, at every point there is a vector, right? That means at every point you will have some value and some direction. Now think this idea in terms of this manifold language. To define vectors at every point on this manifold, that means on the tangent spaces, you will need all the copies of the tangent spaces of the points of all the points in this manifold. So for example, here we have only one point, but there will be other points, let's say P1, P2, P3, P4, and all of these points will carry a tangent space of their own. Alright, and all these tangent spaces with the manifold itself is known as a tangent bundle, and you define a vector field on a tangent bundle, because otherwise all the points will not be included. So this is how the definition of vector fields from real variable calculus or ordinary calculus gets transformed into the manifold language. So let me just write in short, what is a tangent bundle? Tangent bundle just means the manifold itself plus, by plus I mean you are considering them together, so don't mistake it for the ordinary arithmetic operation, and tangent spaces of all the points. Let's say PL. This is a tangent bundle. And if you take a section of the tangent bundle, on that section you can define these vector fields. And a remark about the vector field is that if your vector fields, if they are to be called smooth, then that would mean that on every point that is a vector field is called smooth if it is possible to find curves on the manifold such that all the vectors in the vector field are tangent to the curves. So this is a remark, let me write it down. So smooth vector fields these are vector fields, and a vector field is called smooth if it is possible to find curves on a manifold such that all the vectors in the vector field, by all the vectors I mean all the vectors that is consisting of that vector field. So all the vectors in the vector field, VF means vector field, are tangent to those curves. This is a remark, and in fact these are called integral curves. These are also known as integral curves. And what are these integral curves? They are nothing but the solutions to differential equations. So this is the power of this manifold language. You can apparently link all those things that seem a little bit unrelated to each other and use this manifold language thing, and you can see that they are actually connected with each other. So this is one way to appreciate this new language. And now we have had these ideas of tangent spaces. We know that there are things called vectors, manifolds, all that stuff. Finally, we want to jump into the thing called a directional derivative. So we now want to talk about the last thing, is something called a directional derivative.